Our next panel, entitled The Future of Energy Generation and Storage, will be moderated by David Lin, Senior Director for Future Technology Platforms at the Special Competitive Studies Project. Please welcome our speakers. Dr. David Kirtley, co-founder and CEO of Helion Energy. Tim Latimer, co-founder and CEO of Fervo Energy. Dr. Brandon Sorbom, co-founder and chief science officer at Commonwealth Fusion Systems, and Dr. Eric Wachsman, director of the Maryland Energy Innovation Institute at the University of Maryland.
Hello, good morning or good afternoon, everyone. Hope we're all doing well. It's my pleasure to have this distinguished panel this afternoon to talk about the future of energy generation and storage. We've spent a lot of today talking about the demand side of AI, but now with this panel we can pivot to talking about some of the new and emerging technologies ahead of us that hopefully will solve some of the supply side challenges ahead for AI+Energy. Powering AI will require a diverse portfolio of energy resources. Not a single technology will work everywhere all the time. And so we'll require, as they say, will be a silver buckshot approach rather than a silver bullet. So let's start with this panel, a broader scene setter question and go down the line for your thoughts. A lot of new novel energy technologies here represented on the stage, be it fusion, geothermal, fuel cells, energy storage. All of them require significant upfront capital expenditures to get off the ground. And so I was wondering if you all could share some of your thoughts on what are the most significant challenges in scaling up new energy technologies, and how do we overcome some of these obstacles? Let's start with you, David.
Great, thank you. I'm David Kirtley, CEO of Helion Energy. We're building fusion energy, fusion generators. And I think you might actually hear something very similar from all of us, but for me, for the last 2 years, as we built our 7th generation machine, it's been supply chain. It's been focused on you're building real hardware and you're trying to build big complex systems and you're trying to build it as fast as possible. So it's been supply chain hell. How do you build as fast as possible, get the parts in the door, and then how do you do it from US manufacturers? And so that balance of how do you build in the US, support the US while still moving fast, that has been a lot of the work that we've spent time and the treasure on too.
Tim.
Yeah, hi, thanks for having me. This has been a great conversation so far. I'm Tim Latimer. I'm the co-founder and CEO of Fervo Energy. We're an enhanced geothermal system developer. Geothermal's been around for a very, very long time, but historically it's been limited to very specific geologic locations. You know, think Iceland, where steam is literally coming out of the ground. And the US government has put R&D money into something called enhanced geothermal systems, which is basically using advanced technologies to get higher flow rates out of wells for over 50 years, and made some incremental progress, but our sector had a massive breakthrough last year when we brought on successfully the first commercial enhanced geothermal systems project. And what Fervo has incorporated into the enhanced geothermal system development that's different than what's been done before is using horizontal drilling technology that we've adapted from the oil and gas industry to make it work. So we drill wells 10,000 feet down, turn horizontally, drill 5,000 feet over, and it turns out that's the thing that gets you the right bang for the buck to have cost-effective enhanced geothermal systems today, which removes those geologic constraints and makes it a resource that can be deployed and at the scale of hundreds of gigawatts just here in the United States alone. So it's a proven technology. Our project has been producing electricity for almost a year now at our pilot site in Nevada, and topical to this conversation, our partner on that was Google to power their data center operations there. So this AI and energy conversation is central to what we're seeing at Fervo. When we look at our challenges, actually, to maybe do a contrast, supply chain is actually not a major issue with us because so much of what we do is adopting from the oil and gas industry, which is very established, that we don't really face any supply chain constraints. But where we do face constraints, where I think what's slowing us down the most right now is in availability of capital, number one, and then in some of the regulatory issues needed to get the grid, needed to get interconnected to the grid. So those are the two things that are probably slowing us down the most right now. First off, on the capital side, Geothermal is often referred to as the forgotten renewable. We're left out of financing conversations, policy conversations. So to give you a data point, in the bipartisan infrastructure bill and the Inflation Reduction Act, there were several technologies funded through the Office of Clean Energy Demonstration and other avenues. So nuclear got $10 billion of funding, hydrogen got $9 billion of funding, long duration energy storage got $8 billion of funding, geothermal got $84 million. So we're orders of magnitude lower from a financing support standpoint than other resources, and that's preventing us from growing as fast as we'd like to, even though it's a proven technology. The other piece of this is that getting projects online requires permits, interconnection, and transmission, and that very often is the longest lead time item in our portfolio. So the thing that's preventing us from growing the fastest right now is these transmission constraints, which I'm sure has been a big theme of the day so far. So those are the challenges that we're seeing from really bringing on the amount of power we think we could if those were alleviated.
Yeah, that was a point that Dr. Schmidt raised. 18 years to get a transmission line up and running. That's pretty incredible. A lot to unpack there. We'll come back to it. Brandon, challenges.
Yeah, thank you. So Brandon Sorbom, I'm the Chief Science Officer and one of the co-founders of Commonwealth Fusion Systems, which is a fusion energy company. We're out based in Massachusetts building a commercial demonstration of a device that will produce net energy from power called Spark. And I would agree with David that, similar to, building a large hardware-intensive capital project, supply chain is definitely one of the things that is top of our minds. But I would say another piece of that is actually the supply chain of talent for the industry. There isn't a pipeline of talent that's readily available of people who have built these things before. So we've had to get really creative and look at adjacent industries and say, okay, how can we design our technology so that not just, it doesn't just scale in terms of like the stuff that you need to build for the technology, but in the talent of the people putting all that together. And so we've intentionally designed our technology to try and take advantage of things like, okay, aerospace also builds, large complex systems that have to be integrated. And so I think we have a really big focus on trying to continue, working, with the government in some areas, developing a talent pipeline and really, getting fusion more out into the mainstream so that, there's more people coming through school who are studying it. And there's also people coming from other industries that we can adopt very quickly into the fusion ecosystem.
All right, I'm Eric Wachsman. Besides being a professor at the University of Maryland, I'm the founder and executive chair of both a solid-state battery company, Ion Storage Systems, and the solid oxide fuel cell company, Alchemy. We're different in that we're manufacturing, and so whereas they have to put up a site and, it's a lot of effort and cost to build out that site, for us, it's manufacturing equipment for large volume of manufacturing. And it's difficult because, going back to the supply chain, because China dominates the battery market, well, all of the supply chain for that equipment is in China. It's not in the United States. The other aspect of it, of course, is raising the capital to set up a large manufacturing facility. I'll give you just one example of this. I was an invited speaker at a battery conference in China, and all of the invited speakers had a special dinner. And, it was great. We had really good food, and they passed around some alcohol and all the rest of that stuff. And then they took a break. It was hosted by the regional government, and they started making a pitch. If we were to bring our battery technology to China, they would provide the money, they would provide the facility, they would provide the equipment, they would provide the personnel, et cetera, all of those things. Nothing like that in the United States. I'm happy to say that we just recently won a ARPI $20 million scale-up award, and that's a start. But to get the large-scale manufacturing of batteries or fuel cells, it's a much larger investment, and it is a difficult climate to raise that money.
And maybe that's a great segue. We'll go in reverse order for this next question. Dr. Wachsman, you were talking about the influx of government funding into onshoring, battery manufacturing, and battery innovation. A question for the group: what makes today an exciting time for your particular emerging energy technology? We've been talking about batteries for a long time, fusion, geothermal has been around. Why is now the optimal time to really double down on these technologies? Sir.
All right, well, the need for that has always been there. That never went away, and it never will go away. We always want to develop new things and advance technology. The thing that's exciting time right now is, at least with this particular government, there is an influx of cash to help that. There's lots of programs right now in this administration that will support this technology that has not existed in the past. And so my biggest concern is that that support may disappear. Right now, that's a big reason of excitement. The technology, to me, has always been exciting. I'm doing this for 35 years. I love it. I would never do anything else. But to get that to commercialization requires a lot of capital. And in this environment, it seems like about the best we're going to get.
Brandon, same question. I mean, CFS, Helion are partners in SCSP's newly launched Fusion Commission that we just launched last night. Care to talk about what makes today the optimal time for Fusion to accelerate and move forward?
Yeah, I think it's a really exciting time for Fusion because if there's one takeaway that I had for people in the audience with regards to Fusion is that it's a lot closer than most people think. When you look out in the world, there's a wide variety of opinions. And I think if you look at what's going on inside, especially the more than 40 private companies now that exist that are working on commercializing technology, you can see that the development has just increased exponentially, even in the last like 5 years. And so it's a really exciting time because the technology is now reaching a level of maturity where we know that it's going to work, and it's a matter of getting it to scale, and it's a matter of thinking ahead to the next step of deploying this technology now. And so I think like similar to your comments, we can't take our foot off the gas right now. It's like we're now getting to the place where Fusion is in the realm of we can actually start plugging this into the grid very, very soon. But we need to have the bridge to be able to do that because this is first of a kind technology.
And Tim, please.
Yeah, it's a great question. And why now? I think there's a tech reason for us and there's a market reason for us. And the tech reason for us is there has been a complete technology breakthrough in terms of how drilling is done that has changed the game entirely for geothermal. And to draw a parallel to the oil and gas industry, if you think back 20 years ago, the U.S. was planning to build LNG import facilities because there was this idea that the production of oil and gas in the United States was going to continue to fall off. But what happened? Obviously, the advent of new technologies like horizontal drilling and hydraulic fracturing and more advanced data acquisition completely up into that picture. And now, obviously, we're building LNG export facilities, a complete reversal of what the expectations were 20 years ago. And if you double click on why that happened, it's because the technology around drilling for shale oil and gas got dramatically better, 10 times more effective over the last 10 years. And that was a true technology transformation. And when we started the company, what we realized is that geothermal drilling shares enough of an overlap with oil and gas drilling that technology breakthrough was going to have a similar revolution for geothermal in terms of upsetting people's expectations there. So we set out to prove that you could adapt that drilling technology into the geothermal world and have transformative impacts on the cost structure. And so a lot of efforts like the Department of Energy through the Utah Forge project and then our project that we brought online in Nevada last year with the Google partnership showed that we could actually adapt the technology from the oil and gas industry to drill it through much harder rock, the much hotter rock that you have at granite, and still have amazing drilling performance, oftentimes 10 times better than what prior forecasts of drilling speed would look like. So we've actually reduced our costs from our pilot project to today by over 70%. And so it's put us in a position where we're commercially ready today to deploy. I told you we've got power that's on the grid already. We're building a 400 megawatt project that's cost effective already of 24/7 carbon-free power. And there's this huge upside. And it's hitting the market at exactly the right time because what we're seeing is our ambition on decarbonization is ramping up. There's many markets around the United States now that put in 100% clean energy targets. Many corporate customers, like our partnership with Google, have announced 24/7 carbon-free energy initiatives where they're looking not just for some hours of the year to be decarbonized, but all of them, which requires a variety of resources, as you mentioned in your intro. And then you stack on top of it the amazing amount of load growth that's happening now, not just from AI and data centers, but electric vehicles and onshoring manufacturing. And we are in a growth market in power production for the first time in decades in the United States. And so the market is there, the tech is there, and we are having an absolute renaissance in the geothermal industry as a result.
Timelines for deployment, definitely something I want to get into. But first, Dave, anything to add on the Fusion side in terms of why now?
Yeah, I would say, this conference is great in showing why the upswing in the power market is so huge. The need is there. Honestly, for Fusion, which is clean, carbon-free baseload power that can be sited most anywhere, the market has always been there. The thing that's new that has changed is on the science and on the technology. A lot of the science questions about fusion have been answered, that you can make net energy from fusion. That's answered, done. At Helion, we now have showed that with our approach to fusion, we can pass 100 million degrees. We can reach the core temperatures you need for fusion in systems that are small, that are compact, that you can build in a year or two. We showed that part, but the technology is really the key, is that now the semiconductors, Moore's law happens, it's still going on, or at least enough. And what that has enabled is not, for us, higher speed computing, that's important too, but it's that we can now build the semiconductors that can commute gigawatts of peak power in microseconds, things that we knew 50 years ago we had to be able to do, but the technology didn't exist. The transistor was in the lab. And so now we can do it. We can build those systems. We can build it at a small company in Everett. We can build these massive power systems that deliver this energy. And so that paves the way for the time is now.
Time is now to work on it. In terms of now turning to timelines and milestones for Helion, when will we see a fusion plant fueling the next AI data center?
Yep. Obviously the need is there. And this conference so far has showed that so often the scale of AI comes back to, is there power to power these chips? Are we going to be rate limited in the computation of AI based off of the power availability? That's scary. That's scary for humanity. And so I sure hope fusion can meet that need, because we know fusion can scale. We know that it can scale in power. The question is, can we move fast enough? So at Helion, that's been our focus. How do we build, iterate quickly? How do we do more science? The key is build a machine faster, iterate quickly, build a manufacturing line, have a conveyor belt of fusion. And that's what we have at Helion up in Everett right now. Conveyor belt where the parts come on, and build fusion in a production line, not in a laboratory. And so we announced a partnership last year with Microsoft to build a power plant. Our goal is to have the first electrons on the grid in 2028, and then dial that power up as fast as we can to be able to provide. That system is small relative to everybody in this audience. That's 50 megawatts. And our goal is now, how do we scale that even bigger as fast as possible? We'll get to talk more about that today.
Now, Tim, you've made reference to this already, how you're building Fervo based off of old oil and gas technologies. Could you talk a little bit, and that building off this theme of timelines, it's kind of an interesting dichotomy of using this older technology, retooling it for new and emerging technologies. Can you talk a little bit more about that, and also share some of your plans for Fervo in terms of deploying and scaling?
Yeah. And really, our timeline to deploy has been really benefited tremendously by the adjacency to the oil and gas industry. So very obviously here in the United States, we have a very deep expertise in drilling. We've got great supply chains for it. We have wonderful technicians and engineers that can do that. And so for us, when we go to scale up, we're repurposing a lot of the same drilling rigs that the oil and gas industry is using, a lot of the same tools. 60% of the employees at Fervo we've hired from the oil and gas industry, and they're people who've come over to join us because they're passionate about the technology and they're passionate about sustainability and see this as a new wave. Nearly 100% of the workers we have on our site are actually from the oil and gas industry, because that's the skill sets that we need. And the benefit of that is we're not having to reinvent the wheel on a lot of these things. It's repurposing a lot of this equipment in a novel way to produce carbon-free geothermal energy out of different geology than traditional oil and gas energy. And so we've been able to scale up incredibly quickly as a result. I mentioned we brought our pilot project online last year. It's been producing for nearly a year now, meeting all performance expectations. It was just a small project though, just 3 megawatts. We just drilled 3 wells. We are in the part of our growth journey right now where we're rapidly scaling up. The project that we're building in Utah now is a 400 megawatt project, so nearly 100x scale up from our pilot project. But the great thing about us scaling up there is it doesn't require us to completely redesign the system. It just requires us to drill more wells. And so we've gotten huge improvements in productivity of our wells year over year. And we're now about halfway done with the first phase of that project already. So that's going to come online in 2026, just a couple years away. And as we think about the future, what we've done with the technology we've unlocked is drop drilling costs so low that we can go really deep now to access that high temperature rock in a lot of locations. And so it changes where the geothermal industry is today, where we only have about 4 gigawatts online in the United States, to something where there's hundreds of gigawatts of potential. And so we're shortening our construction timelines, increasing our drilling timelines, and we have a roadmap where we think this is something that produces single-digit gigawatts of new geothermal this decade, double-digit gigawatts of new geothermal next decade, and then hundreds of gigawatts into the 2040s and beyond, and becomes a really meaningful part of the energy mix. And that's the timeline that we're working on. And I think what's exciting for us is we're already on that learning curve because we're learning through deployment because these projects are in the ground and we're iterating and coming down that cost curve, much like we saw with solar and wind over the last couple decades today.
Brandon, we've talked about challenges for fusion, supply chain, talent. On the supply chain piece, if fusion were available tomorrow, what parts of the infrastructure do you think would be most unprepared to take it on?
Yeah, that's a great question. I think one of the advantages of fusion is that because it is a firm, base load, large power source that's thermal, you could actually replace existing and retiring thermal power generation. Like if you took a coal plant site, it already has the grid interconnect, it already has the switch yard and the turbine, and what you're really doing is you're replacing the heat source in that. And so one of the advantages is that you could look at the network that we have of power plants that exist today and look at the planned and maybe accelerated retirement of some of those power plants and look about replacing those with fusion power. And I think in general, the challenges, when you ask about the grid being prepared, I think really the electrification of the grid as a whole and the interconnection of the grid as a whole is something that also we would want to accelerate for fusion, because fusion is going to be able to plug into the existing grid that we have already. And so I think we need to continue to accelerate how our existing grid is connected and can support things like electrification of vehicles.
Yep. Eric, again, on timelines for energy storage, on what, if any, timeline will advancements in energy storage enable it to take on the workloads that were traditionally reserved for baseload power?
Well, energy storage is not by itself is not taking over baseload power. The fuel cells can take over baseload power. The energy storage is tied with either wind or solar to do that. And I would say actually the best option for distributed generation is a combination of all of those, where you have a baseload from the fuel cell, you have the wind and solar, which are going to go up and down depending upon wind speed and solar radiance. The battery can store that, okay? But as far as when it's going to get to, these types of large-scale data centers, we have to start at a smaller cell right now, which we plan on having available next year for the Department of Defense. That will then go to consumer electronics, and then it'll go to EV, and then it'll go to grid-scale storage. Each of those jumps in technologies, a jump in manufacturing volume, and as I mentioned before, that's primarily the limitations, raising the capital. Our battery is quite different from all other batteries. Solid state is different from all other batteries, but our solid state is different from all of those, okay? In that one, it's non-flammable. That's a big issue with batteries. You might have seen battery fires. You can't put batteries in Manhattan because of the concern about them catching on fire. Well, we use a ceramic electrolyte, which cannot catch fire. They have higher energy density than conventional batteries, so your range or time of operation is longer, and they have no expansion, contraction like conventional batteries. You may not be aware of it, but they actually expand and contract when they're doing it, which allows you to pack them much more tightly, okay? But the other thing, which I think is really important, we start getting to the grid scale application or AI for computers, is that they're able to operate over a very wide temperature range, right? So you may not be aware of it. There's a lot of lithium-ion batteries that are going out there right now providing backup storage for AI, for all kinds of things. And they're using conventional lithium batteries. And that has a liquid electrolyte, which has a very limited operating temperature range. If it gets too cold, the conductivity drops off and they don't operate. And if it gets too hot, it catches on fire. With the ceramic, that temperature range problem isn't gone. And so what they're doing right now, I happen to have a Tesla as an example. I have a cooling system to maintain the operating temperature of my battery. That's a parasitic power. And so if you want to store energy and you're getting it from whatever source it is, you want as much efficiency as possible. But if you're using a significant fraction of that electricity to just maintain the operating temperature of the battery, well, that's an efficiency loss. And so we can actually have ours operating out in the full sun with no air conditioning. You don't have to have this big container that you're controlling temperature at.
Yeah.
The other aspect is, which was brought up earlier today, is a supply chain of materials. So yes, right now our current one is a lithium-ion based one, is a lithium battery based one. We have the same technology for sodium. And in the case of the solid-state sodium battery, sodium is one of the most abundant elements in the earth. I mean, go to the ocean, right? It's everywhere. There are no rare earths. There are no resource-limited elements in that battery structure. And so that provides a much lower cost, which ultimately cost is important for everything. And for this particular application, I think cost is going to be paramount.
Good. I want to pivot the conversation now to talk about innovation, how to accelerate innovation in your respective fields. And I'll start with you, David. What policy changes do you think need to occur to really support the rapid deployment of fusion energy?
Yeah, I appreciate this one. I think when we started Helion, we spun that out after we had demonstrated we could do fusion at small scale. I said at the time the existential threat to our technology company, in fact, all of fusion, was regulatory policy and then general policy around power. Part of that is solved. And this is reasonably new news that last year, the Nuclear Regulatory Commission said fusion is not nuclear power, which is pretty outstanding and amazing. That was codified into law this year with something called the Advanced Act, separating fusion from nuclear fission. That fusion doesn't go critical, doesn't make nuclear waste, and that radically changes the picture. We're regulated like a hospital. And Helion's been regulated by the Department of Health on the nuclear side, on the safety side, since 2018. We've had a long history of that. So that's solved. But what we uncovered after that, as we started to work towards this Microsoft power plant, is there's a whole nother body of policy that is slowing down the deployment of power. That won't be a surprise to the other people here, but it was a surprise to me from Fusion because we had been so focused on building and demonstrating the technology, is that the deployment timeline for new power plants is tremendously long for a bunch of reasons. Even in a case like ours where you don't need to build a lot of new transmission line, still deploying power plants is really tough. We've been working on the state of Washington where we're deploying this this facility for Microsoft on who is going to regulate fusion. What is the path there? And so we're still solving that right now. There's a fusion energy working group within the state to get all the agencies together to make sure there is a clear path of what is even the process, so that we don't have, technology is ready, let's not go spend a decade figuring out how to build a power plant. So we've been working now for the last few years on siting, interconnects, how to plug into those existing substations that are there and ready to accept the power, but we don't know how to do it yet. And so policy that we're focused on is actually streamlining that permitting and interconnect timelines. We can talk about manufacturing, I pointed to that too, but then we're spending a lot of time thinking about how to accelerate US innovation in manufacturing and onshoring technology as well. Those are the two big categories that we're focused on at Helion.
Tim, how does Fervo's approach to geothermal seek to overcome the traditional limitations of the industry?
Yeah, our approach, really, if you look at what has kept geothermal from scaling in the past, it's what we call exploration risk or uncertainty about the development process. What you find is that a lot of times, unless your geology is Iceland, you've got to drill deep areas and hope that you intersect something that has both the temperature and the flow rate necessary to produce geothermal at sufficient quantities to be economic. And what we found over the last 50 years of geothermal development is that only happens some of the time. And of course, investors don't like things that only work some of the time because that doesn't make for a great investment profile. And that's how we find ourselves in the world today, where geothermal is less than 1% of the electricity mix here in the United States, even though it has all these attributes that everybody likes, 24/7 and carbon-free. And the issue is that a lot of times when you drill those wells, you just wouldn't intersect that high flow rate that you need. And so Fervo's approach is very different. It builds on fundamental research that was done going back 50 years ago at the Los Alamos National Lab and all the way up through today that the Department of Energy's led with the Utah Forge project on enhanced geothermal systems, where rather than trying to find natural flow pathways for the geothermal fluid in the reservoir to heat up, you can create them through processes like hydraulic fracturing that's borrowed from the oil and gas industry. And what we have done differently is drilled these wells horizontally so that we can basically create giant heat exchangers in the subsurface that mean that we can actually engineer a well to be successful every single time and eliminate that dry hole risk. And so if you take something that's incredibly valuable because it has these attributes of being 24/7, carbon-free, low land use footprint, and it's fairly cost effective, and then you eliminate that risk that makes it hard to raise capital, which is what we've done by bringing technology solutions to the table that eliminate that risk, what you find is a project and a resource that's really actually able to attract capital and take off. And so what we've done is develop new ways of drilling using that horizontal drilling technology, radically drop the cost of drilling, and turn geothermal from something that works some of the time to something that works all of the time. And that has fundamentally changed the scalability of this resource.
Maybe a quick follow-up there. What geographic limitations are there that you're encountering?
Yeah, it's an interesting question. There's no binary geographic limitation. It's not like it will work here and it won't work somewhere else.
Okay.
You can actually think about it a lot like solar. You know, solar has a wide cost range because some places are a lot sunnier than others. Geothermal is the same. And when we think about geographic limitations, what we look at is how deep do you have to go to hit a certain temperature? So we design our power plants to work at around 400 degrees Fahrenheit. We've sited our first projects in Utah and Nevada because we can actually achieve that temperature only having to drill down about 9,000 feet. If we were to try to do something like that here, you'd probably have to go closer to 20,000 feet. And so it's not that it's not doable, it's just a question of how rapidly can we drop drilling costs so that we can get there. So our model for the future is we will develop several gigawatts of power in the markets we're in today: Utah, Nevada, Idaho, Colorado, places that are favorable for deployment. But what we expect is that's going to allow us to, through deployment-led innovation, drive costs down so rapidly that it becomes in the money to develop in places like the Eastern United States, expand internationally. And that's the kind of cost reduction and productivity increase that we envision will unlock a resource that's truly hundreds of gigawatts for geothermal in this country, and turn it into a resource that can be developed, not just at a really prime site in Utah, but really across the whole country.
Brandon, similar question: is fusion constrained by geography? And on top of that, what are some other innovations that can drive fusion deployment?
Yeah, so I think fusion also is not constrained by geography. You can put it anywhere that you, really anywhere that you can put a thermal power source, which is pretty much everywhere. You want to have a grid interconnection for that because the power plants are going to be pretty large. But yeah, there's no fundamental constraint with the geography. And as far as innovation, I think there's a couple different flavors that comes in. One of them is financial innovation with the government. So for example, there's a bunch of initiatives that have been started. One of them is the DOE started what's called the milestone-based cost share program. This is actually similar to what was called the COTS program for space, which is why we're flying astronauts up to the space station in US manufactured rockets as opposed to foreign manufactured rockets. And it's basically a way for the government to have a cost share with the private fusion industry in getting that technology out to market. And so right now that's, the first phase of that has been funded, but I think it would be really great if the rest of that program, which goes into a couple $2 billion, was funded by Congress. And that would really unlock, I think, a lot of innovation in companies, as the government is helping out these companies develop the technology. And like David mentioned before, really supporting the rapid iteration cycles that are required to get this technology out into the market. And I would just really quickly add on the technology side, I think a way that especially the government can help is to continue to focus the priorities of the basic science research that the government does, through the DOE programs, for example, into technologies, really being in lockstep with private industry. And as private industry is developing commercial technology that will be deployed out into the grid, for DOE to have basic science that supports the iteration of that technology and continually making that technology better. So for example, building, a fusion prototypical neutron source, which would be a big national lab type facility that would allow us to rapidly iterate on the materials that we use and continue to improve the efficiency of the plants that we build.
Speaking of raw materials, so Eric, AI, there's been a lot of research papers being written about how AI is reopening a whole opening new possibilities in terms of battery chemistries, battery design. What are your perspectives on this? What are some of the more exciting battery innovations that keep you waking up in the mornings reinvigorated about the sector?
Well, I hate to say it in this audience, but I've never used AI. So, everything that we've done has just been an idea that came to my mind, and we made it work. I understand that it has the potential for accelerating materials development, for example, and there was a lot of interest in doing that. But again, that's something that's at the early stage, and it's going to take a long time frame before that gets into a battery and then scales manufacturing. And if we're talking about energy for AI, then I think you need to focus on some of the technologies there right now. Don't wait for AI to create a better battery. Make the better batteries we have today work for AI.
Now, just a couple minutes left, but I did want to ask each of you, especially our CEOs and founders on the stage, if you could describe that aha moment that really inspired you to establish Helion, to establish Fervo, or even for Brandon and Eric, inspired you to work on fusion or battery technologies. What was that? Is there, or can you think about that light bulb moment that really inspired and shaped the way you think about energy technology? David, please.
Yeah, I think I'll take it a little bit different direction to start off already. Is that to me it was, fusion was this thing that if we could solve, if we could crack it, we knew the scale, we knew what it could do since childhood. And if we have more time, I'll talk about my childhood. But that it was an answer, or the answer. But I remember being in the lab, actually. I remember sitting on, working on our, this would have been our second generation machine, where the first time we were able to take this small scale system, and I say benchtop for the people in this audience, but it was like still a big warehouse, and take this fusion fuel and superheat it up to 10 million degrees, sort of like the cusp of where fusion really starts, and then measure like, wow, those are fusion reactions. That's a ton of fusion that's happening, and it happened in this little machine with cobbled together funding from various government grants for a couple $1 million. And I said, holy shit, like we were able to do that here for a couple $1 million. Let's figure out, this has to scale. So let's go figure out how to make it scale. And let's tackle the engineering to minimize the amount of new science we have to do so we can move faster. And that was that moment. And I think it was like late at night, 8 p.m. on a Friday night where I should not have been in the lab. But, and then that told me like, this is the path forward. Let's go do this. Let's go tackle this. Really cool. Yep.
Tim, what about yourself? Were you digging a hole in the backyard?
Yeah, I was. And I thought, wow, what if this could just be 10,000 feet deeper? Yeah, I was digging a hole actually, but it's in a different context. So I'm from Texas, and I went to college at the University of Tulsa in Oklahoma and studied engineering there, and graduated at a time when the shale boom was absolutely taking off. So me and practically everybody I knew found ourselves working in the oil and gas industry a little over a decade ago. And so I was working as a drilling engineer out on a rig in South Texas, in the Eagle Ford Shale. And there's a wide variety of temperatures in the geology in oil and gas, and the Eagle Ford happens to be one that's pretty hot by oil and gas standards. It's not hot by geothermal standards, but it's hot by oil and gas standards. And we were having equipment failure in our motors because the temperature was too high. And so my first ever job as an engineer right out of college was, this formation's really high temperature. Can you figure out, how we solve that? So I'm doing a lot of research online about how you deal with high temperature drilling, and a bunch of papers pop up from this thing called geothermal. And I had no idea what it was at that point in time. But I got pretty captivated by it, and I start reading more and more and more about geothermal. And I found this pivotal report that was published by MIT in 2006 called The Future of Geothermal Energy. And it outlined this roadmap, how enhanced geothermal systems could become this ubiquitous resource all around the world to provide reliable carbon-free energy, but there were fundamental technical challenges that needed to be solved. The principal ones of them were, how do you get high flow rates out of low permeability formations, and how do you dramatically drop the cost of drilling? And I'm like sitting on a drilling rig in South Texas looking at this, and I was like, wow, in the 7 years since they published this report, this problem actually got solved completely, but by a different industry. And the light bulb went off for me, and I just became completely obsessed with the idea. And then the more I thought about it, the more I realized that as we were facing these issues with sustainability and climate change, and I wanted to move my career in a direction that was going to be more aligned with that, it felt like cheating that I found the one renewable energy industry that required drilling engineers, the thing that I knew how to do and that I'd learned how to do. And I realized that could be a huge benefit for getting buy-in, moving to the market faster, and thinking through what this would look like for the energy transition and the workforce transition, not only for myself, but for everybody else that I knew that worked out there. And it's been a decade-long obsession ever since. So that was the light bulb moment, and it's pretty gratifying to realize that it worked.
Great story. Brandon?
Yeah, I think so. I came from a team that had been working on this technology for a long time, and in the lab and in graduate school at MIT. And I think the aha moment for myself and the other co-founders came. We were actually at a conference in 2015, and we had just published a paper about how you could take this proven science from a fusion device that was being built. That's this international collaboration still being built in France, and it's this giant device. And we had come up with an idea to shrink the size of that device pretty substantially by using some new materials technology. And we were at this conference, and my advisor was giving a presentation on this, and just the reaction that we got from the crowd even surprised us. We thought this was a pretty cool idea, but the reaction from the crowd really surprised us. And we were like, oh my gosh, we should actually figure out, it's great to publish a paper on this, but we should actually figure out how to build this thing. And so a bunch of us that night said, okay, what's the smallest device that we could actually build with this? And so people started trading around, things generally start on spreadsheets. So people started trading around a spreadsheet that night, which then turned very quickly into, getting CAD drawings and doing more deep analysis. But I think that was sort of this catalyzing moment of, we were all sitting together at this restaurant, and we were all of us at the same time, we're we have to actually build this.
As the saying goes, all great ideas begin with a Microsoft Excel spreadsheet. Eric.
All right, well, since I founded two companies, I have to tell you two aha moments. So the first was when I was a graduate student at Stanford, which, if you look at my age, was a long time ago. I came with an idea of how I can make a highly conductive material which was not stable by modifying the cathode surface. And I spent 20 years trying to just get the funding to advance that from an idea to a working device. And it now has, anywhere between 4 times the power density of anything in the literature to 20 times the power density of anything commercially available today within solid oxide fuel cells. The second aha moment was then later on, because again, it's funding cycles the Department of Energy had in fuel cells. When I went down, so while it was down, I thought, well, let me look at batteries. And the aha moment there was that same structure that I developed for the solid oxide fuel cells would work for a solid-state battery, and that's the basis of my solid-state battery company. Waste.
Well, that's a great note to end on. I invite all of you to join me in thanking our panel of distinguished experts. Thank you all.
Yeah.